Hello there, everyone. Welcome. We are so glad that you are here. We're gonna thank you for your patience. Hello there, everyone. So we're welcome. We are really glad you are here. We are going to give people just a couple minutes to get in. Thank you for your patience with us getting the Zoom set up and that type of thing. We are streaming this, which we are excited about. As you can always catch, look for our videos on YouTube, where you can see previous talks and whatnot.
Apologies to everyone about the passcode. There was not supposed to be a passcode. I usually don't set up a passcode. And so my apologies to everyone for the confusion on that.
Zoom. Zoom. I feel like we have really good luck most of the time, and generally things, we go pretty darn well if you ask me. So that's good. All right. So I think let's do just a few tiny introductions or tiny announcements as we're getting set up. So welcome to the first meetup of the Salt Lake City R user group of 2025. We are really glad that you are here. I imagine that most of you did in fact find us through Meetup, but I am just gonna drop the link again here for where to find us. You can see we've got um, some upcoming events with some great speakers. So we have a mix of events that are done over Zoom like this, which are talks, and then in real life events for people who are in the Salt Lake area that are more networking and social and like getting together kind of time. So we'll be doing several of those over the coming months. We are supported by the R Consortium, and we're really grateful for their support. And we use the R Consortium's code of conduct, community code of conduct. I'll drop a link to that here. But this is a friendly and professional space, and we both Andrew and I will be moderating, and we are really glad to welcome you into this space. I'm super excited about our talk today, and so I'm going to give a little just bit of an introduction. So Simon, our speaker today, is a software engineer at Posit, formerly our studio, and Simon works on open source statistical software. Like Simon's academic background is in statistics and sociology, and one of the things, Simon, I really appreciate about you and your work is how you think about tooling and like how it does help us think about data. So Simon works on a number of R packages, some of which you're going to see on the slides here, and um, get to talk about a little bit. And you can, if you want to see more from Simon, there's a link to his blog on the meetup page for this. So Simon, thank you so much for coming. We're really glad to have you here. Thanks for, you've got your screen shared, which is great. As Simon goes through and gives his talk, which we're excited about, feel free to type questions as you go along, and we'll maybe bring them to Simon's attention during the talk if that's appropriate, and we will have time for questions at the end as well. So Simon, thank you for being here. Take it away. I'm excited to hear more about this.
Yeah, thanks so much for having me. So I'll just assume y'all can hear me and see my
You
slides,
sound
and feel
great.
free to
Yep.
interrupt if
Slides
not.
look
Okay.
great. Yeah.
So I'll start this talk off with a story about a job that I had when I was in college. This is me in college, and to be anatomically correct, I did have hair in college. I worked as sort of an R helper at my university. So faculty and students from the social sciences and the life sciences would come in with R analyses that they were working on and ask us questions. We would help them write code, help them debug code, interpret statistical results. And my shifts in this role were like an hour or two long. And it was kind of like camping outside of the concert style. Like we'd show up to these shifts and there'd be people like with their laptops ready as we unlock the door and like come in with us, and we just like hit the ground running. Um, Especially when folks would come in with the idea that they were going to be fitting statistical models, we would spend often like 45 minutes or something of our hour together just waiting for those models to run. And that's really not what those folks were there for, right? Like they would come to these office hours so that we could write code together, so that we could iterate on the results that we got back, so we could interpret statistical models. And so during those sessions when that code would take most of the time to run, it often felt like we didn't get a lot done. And so I came out of that, over time, more and more emphasizing in my kind of advice for them, like we're going to focus on the techniques that will complete as quickly as possible so that we can spend as much of our time as possible iterating on the modeling pipelines that we put together. And so from that job, I learned that progress is made when the R session is idle, right? Like when the model is running, there's not a lot we can do in terms of interfacing with it, but once it's completed training, we can make use of tools to interactively develop that machine learning pipeline. Another job I had in college was on the tidymodels team as an intern, and this time the computer was facing me. In the second half of the summer, I was working on an R package called Stack, which is a package in the tidymodels for model ensembling. And if you're unfamiliar, the idea with ensembling is that you take the output of many diverse statistical models and you find some sort of way to combine their predictions to generate more accurate predictions. This often means that the models, the ensemble models predictions are more performant than any of those constituent models, but it's also much more computationally intensive. Like instead of fitting one model, you're fitting N, and that takes N times as long. So of course, like Posit offered me their sort of standard issue laptop for the summer to use, but I didn't want to be a burden, and I already had my R set up on my laptop that I had bought off a buddy in my sophomore year of high school for like $300. And it turns out I probably should have taken them up on this offer to use the standard issue laptop, because I'd have these experiences of like prepping code to run during a lunch hour or overnight that I knew I could probably send to one of my coworkers. And I often did, and that could finish in 10 minutes or something like that. So that would allow me as an R developer to make progress much more quickly on the package that I was developing. And so this is another lesson that I've taken with me as I've joined Posit full-time on the tidymodels team developing statistical software, is that fancy computers are not a given. I happen to work on the sort of standard issue laptop from Posit now, but when something takes me 30 seconds to run or a couple minutes to run, I know that can often mean that it will take many of our users, up to an hour or something like that, depending on the kinds of machines that they're working on. So these two gigs, I kind of learned lessons that I still keep with me now as I'm working on the tidymodels packages, and thinking about the ways that our software can make data scientists more productive, is that progress is made when the R session is idle. And so preferably, that code finishes as fast as possible and lets people iterate on their modeling code. And also that fancy computers are not a given. So when I see a slowdown on my fancy computer, I should be concerned. These two bits of motivation have helped me in the last few years cut down on a lot of the overhead associated with using tidymodels packages. And at the same time, before I even joined, there are all sorts of optimizations that tidymodels makes, such that if you use the packages instead of the underlying engine packages that the tidymodels relies on, you'll see a lot of speed ups because we've implemented all sorts of tricks under the hood to cut down on that elapsed time that you'll see when you're developing machine learning models. And so now that I've given a little bit of background on my motivation here, we'll jump into an applied example. This example is based on a book that I'm working on called Efficient Machine Learning with R, and it's early drafting stages, but I hope that what's currently live is helpful nonetheless. If you are interested in learning more, I actually can't find the chat. So maybe, Julia, I can have you send the link to the repository for this talk. That repository has links out to the slides that I'm speaking from, as well as this book that I'm referencing called Efficient Machine Learning with R. So the book is based around this applied example that I'll be talking through in this talk. In the introduction of the book, I walk through 4 changes you can make to your tidymodels code, often in as little as 7 lines of code that can greatly reduce the amount of time that your tidymodels code takes to run without sacrificing predictive performance along the way. And so in this talk, I'll walk through that introduction at a higher level to give you a taste of what's in that book. If you're interested, then you can go on and read the introduction. And if that's not enough, each of the 4 chapters following that introduction delve into the 4 sections that I'll talk through today in more detail. But let's actually introduce what that applied example looks like. So imagine we're working in a predictive modeling problem. We have a data set, 100,000 rows and 18 columns. So 17 of those columns we'll use to predict a binary outcome variable or a target. And that outcome variable takes values yes or no. So we want to use the information in those remaining 17 columns to predict the value of that outcome. And those predictors can either be numeric or categorical. And as it happens for this example, I've set a few traps that often lead to computational slowdowns with many modeling engines across R and other computing platforms. So the question we'll be poking at is, how long does it take to tune a boosted tree model on my laptop? So when I say tune, what we're going to do is try out a few different arguments for ways that we could parameterize this boosted tree. We'll try out 10 of those and we'll fit them to 10 different resamples. So we'll take the 100,000 rows and cut up subsets of it. And as a result, we'll fit 100 models. So each of those 10 configurations will be fitted to 10 resamples. So the thing I'm estimating is how long does 100 model fits plus some predictions and some data processing take. If you're unfamiliar with a boosted tree, really the most important point for this talk is that they tend to take a while to fit, but they're based on fitting a bunch of decision trees one after the other. And as you move along in that sequence, newer decision trees are trying to correct for the errors that the earlier ones had made. So in the tidymodels, the code that you need to write to tune a boosted tree model is something like 4 or 5 lines if you just make use of all of the defaults and the sort of standard rate search method, which is grid search. When I run that code on my laptop using a default engine, which is XGBoost in tidymodels, that code takes something like 3 hours and 40 minutes to run. There are all sorts of metrics that we could use to measure how well that model performs in terms of its predictive performance. But for the sake of this example, I'll use the area under the ROC curve, which takes values between 0 and 1. And so in that example, we see an area under the ROC curve of 0.8957. So values closer to 1 are better and vice versa. We can make a few optimizations to this code based on our intuition to cut down on that computational time a lot without really sacrificing predictive performance. So I had to change the number of significant digits by default that R prints here to show any change in that area under the ROC curve. We see that predictive performance drops from 0.8957 to 0.8954. So very, very small change in performance. And instead of 3 hours and 40 minutes, we're looking at 90 seconds. Eric, I appreciate the look of shock. That's much, So we're seeing basically virtually indistinguishable performance in fractions of a percent of the time. And we can consistently make optimizations like this while we're using the tidy models with a few pieces of intuition. And this is what my book is based on, is trying to develop uh, a set of pieces of intuition so that you can just pull those out of your back pocket, cut the time down by a factor of 4 or 10 or whatever it may be, and allow you to iterate faster. So in that 0.7% of the time, you might have seen in the abstract, I talk about 145 times speed up. That's just 1 over the 0.007. And if you want to confirm that, all of the code to run that yourself is publicly available in the introduction chapter of that book. So how did we do it? We made 4 optimizations in this case, and we did so using 7 lines of code, either changing code or adding lines. And we'll walk through each of those changes. I'll talk through conceptually what the difference actually is, and then I'll show you the code that you need to make that happen. Before we dive into that, though, I want to give a little bit of background about how tidymodels actually works, because this will really help us wrap our heads around how to make tidymodels run faster. So when you call code to fit a boosted tree with tidymodels, which is shown in the gray at the top of this diagram, that code looks exactly the same or almost exactly the same, regardless of the computational engine that you're using underneath the hood to fit that model. So the tidymodels team doesn't actually write the code to fit the boosted trees. The XGBoost team does that, the LightGBM team. The nice thing about working in R is that there are a lot of very knowledgeable statistics practitioners that also work in the language and implement the models that they design in the R language. So the really nice thing about that is that there are all sorts of models available, and if we can put a layer on top of that so that the syntax is exactly the same, then we can access all of those different what we call modeling engines, or the packages that actually implement the training and the prediction code. The blessing and the curse there is that all those different people have different opinions about what modeling software should look like. And so that's where the tidymodels comes in, is that we put a layer on top in order to standardize the interface that people work with, so you can quickly iterate on your modeling pipelines without having to understand the minutia of the interface. So in this diagram, we're looking at the elapsed time that a model may take to train on a sort of timeline. In the portions shown in green are sort of tidymodels' fault, if you will. Like, we're responsible for the amount of time that this code takes to run. And it doesn't take very long at all. Like, tidymodels isn't really sensitive to the size of the data. It's just like pushing around small relational data structures so that we can translate from the syntax that you provided into the syntax that the modeling code uses. And then the portion shown in orange is the time that, or is what I'm using to represent the time that the model takes to actually evaluate training on the model. So in reality, the portion shown in green, this diagram isn't to scale. The portion shown in green are fractions of a millisecond. And we've done a lot of work to cut that down to basically nothing over the years. And so especially with a modeling engine like XGBoost, we're talking about fractions of a percent of the total evaluation time. And I kind of prove that in the book if you want to call my bluff on that. So this is helpful intuition to understand how this actually works when we translate back to our problem of tuning a boosted tree model. So again, we're trying out 10 different ways we could fit a boosted tree. And the way that we're trying those out is fitting them to 10 different subsets of those 100,000 rows. So The tidy model still has these portions in green where we're translating syntax. And then we're evaluating 100 boosted tree models. 10 different models, and each of those 10 are tried out on 10 different subsets of the data. The first thing we can do to cut down on that training time is to distribute computations across cores. So M series laptops from Apple, those laptops usually will have like 10 or more CPU cores, and many of the peers to those laptops that are running Windows and Linux often have similar ballpark numbers of cores nowadays. But again, fancy computers are not a given. Even 10 years ago, a 4-core CPU was relatively common. So that's what we're going to be making use of in this book chapter. Instead of fitting all of these 100 boosted tree models one at a time in order, we can distribute each of those 100, so 25 at a time. I'll toss those off to one core, another 25 to a second, and so forth, so that all those fits can happen at the same time. And in order to make that happen in tidymodels, you need one-line code. We integrate with a framework for parallel computing in R called Future. So if you've used Future, this is probably familiar to you. This code basically sets up all the communication you need with tidymodels so that when you run your tuning code, tidymodels can detect the information it needs and distribute computations in the way that you've specified. Okay, so that's our first optimization. Best case scenario, if I distribute computations across 4 cores, I see a 4 times speed up. In reality, it's a bit more complicated than that. I encourage you to check out the parallelism chapter in the book if you're curious. The next thing we can do is move on to a different modeling engine. So like I said earlier, I tossed a couple traps into this training data when I simulated it to trigger slowdowns that I know happen to be the case for this default modeling engine, XGBoost. And those things might be the case for the data that you work with in your roles as well. If we have good data about the kinds of things that introduce slowdowns with different modeling engines, we can choose ones that will be most resilient to the shapes and sizes of our data and cut down on that time to train. So in this diagram, instead of each of those individual 100 model fits taking a minute, they're taking 30 seconds. So in this case, I'm transitioning from the XGBoost modeling engine to an alternative framework in R called LightGBM. You can call this a changed line of code or added. Beforehand, I just used the default, so I didn't actually type out the engine equals XGBoost, but you can do the math as you will. So far, we're still carrying out all 100 model fits. For many different machine learning models, on the way to training one model, you're also training many other parameterizations of that model along the way. So earlier, I described training a boosted tree model, as in you train one decision tree, and then you train another to correct for the first one's errors, and so on and so forth. And so one way I could set up a boosted tree model is to train 1,000 trees. But on the way to training 1,000, I train 999, 998, and so on and so forth. And so many machine learning models support what we call the submodel trick, where I train a model on 1,000 trees, but I can also evaluate models on the way to those 1,000 trees. So I can evaluate a model with 10 trees and 100 and 500, even after only having fitted that model with 1,000. If I had just naively implemented that code myself, then I'd be carrying out all those fits that happen to happen along the way, but that tidymodels will just automate away for you. make that happen underneath the hood. And so in this example, we can set up the grid that that define the models that we're interested in evaluating, such that we can fit a third as many models. So instead of fitting, well, I said 10 earlier, but it's actually 12. Instead of fitting 12, I can fit 4, but evaluate all 12 because I've fitted those additional 8 along the way to training before. This is a couple added lines of code. And I go into more depth about how this works and what it does in the book chapter. And I will say, in some cases, this just works. If you're just training one parameter for a given model, and that parameter happens to support this trick that we call the submodel trick, then this will just kick in underneath the hood without you having to do anything. What we're actually doing in this case is using specifically a regular grid, which will set up the possible models that we're choosing between in such a way where we can hook into this submodel trick along the way. We have one more optimization to walk through, which we call racing. So now I'm fitting a given number of models. I'm making use of the submodel trick to cut down on a good few of those, but it turns out we can cut down on even more. So let's walk back to when I said we are choosing between 10 different models, and the way that we're doing that is fitting them on 10 resamples each. So we're carrying out 100 model fits. Let's imagine there's no submodel trick happening. One way that I could do that is fit each model on all 10, call it good. Another way is I can fit each of those 10 models on the first 2 resamples. So I fit it on one subset of data and then another. And then I look at how it's doing. And using a repeated measures ANOVA model, statistical analysis, if you're like, what the heck was that? We can determine that it's very unlikely that some of those models will ultimately outperform others. So maybe after I fit these models to 2 resamples, I can determine that 5 of them are very unlikely to outperform the other 5 based on the metrics we've calculated. So then I go on to the 3rd resample, and I only fit the models that are remaining, that we're not given up on early on. And maybe now that I have more data after that 3rd resample, I can determine that another 3 of those are probably not going to outperform the top 2. I'll go ahead and toss those. And at that point, I can just fully resample the remaining 2 until I'm confident that one is going to outperform the other. And so using this method, we can cut out many more of those model fits such that instead of 100, we're talking 30 or 40 or something like that. In tidymodels, this is just one changed line of code. I guess this is kind of cheating because you also need to load another package. But instead of a tune grid, which does a default grid search, we can use tune race ANOVA from the find grid package. And so that's the last trick that I'll talk about today. These 4 tricks all together in the example that I talked through in that introduction chapter bring us from an initial evaluation of our boosted tree models of 3 hours and 40 minutes to 90 seconds. And that's a complete game changer in terms of our ability to iterate in order to diagnose the model and interpret coefficients and so on and so forth. If you're interested in learning more about the tidymodels, if you felt a little bit overwhelmed by the pace and the content of this talk, I would encourage you to start off with the book Tidymodeling with R by Salt Lake City's very own Dr. Silgi. This is a great book to start off if you're a Tidyverse user already, but are just getting started with machine learning with R. And once you've worked through this book, you're totally ready to go to dive into the book that I'm sharing about today, which is called Efficient Machine Learning with R. we're looking at the homepage for this book right now, but I'll just scroll down to this outline. This talk is based on the introduction, and the introduction walks through the 4 steps that in those next 4 chapters I dive into more detail on. So the book is, again, in its early drafting stages. Each of these 5 chapters have a good bit of content in them. And at this point, I'm kind of thinking through how to reshape. I'm focusing a lot on the models chapter right now so that we have high quality benchmarks for all of the engines supported by tidymodels. But even to just get started with the introduction to that book, and to see practically in more in detail how you can actually implement these in your code is a great place to start if you're interested in working from here. If you're interested in doing so, you just want to save one link, I would encourage you to check out this repo that I set up at github.com/simonpcouch/SLC-RUG-25. This has source code for the slides that I presented today, and links out to all sorts of resources, both tidy modeling with R and efficient machine learning with R, as well as a few different places that we've written about performance publicly related to tidy models in the past. I just wanted to end this talk by saying that I feel very grateful to be able to drop into the Salt Lake City RU user group for the 3rd time. I always enjoy coming by.
Thank you, Simon, and thank you so much for coming by as well. That was really interesting. And I mean, that is dramatic. That is dramatic.
Yeah, pretty significant.
Yeah, nice. So if you are here with us, and you've got questions or follow-up questions, you can go ahead and type them, or if you want to use the raise hand feature, we can do that as well. Simon, I want to start off with a higher level question that somebody asked that I thought was kind of interesting, that might like to kind of see what you may have thought about. So somebody saw the racing procedure and kind of saw like an analogy or a parallel. It's like, oh, that's sometimes what happens when venture capitalists invest in a bunch of startups. It's like, okay, you all go try and then see which ones do good and which ones aren't, and the ones that aren't good, like cut off and then keep investing more in the other ones, which I think is very interesting. Like, it's like, oh yeah, no, that's a great analogy. As you have been working on these strategies, like different kinds of strategies, do you find any particular like analogies or ways of thinking about them helpful for understanding what they're doing, or for knowing when to reach for one? This is a very high level question, but I'm wondering if you have anything like that, like any sort of like analogies, or this is like when we do X, or does anything come to mind for you?
I love the analogy of the venture capital. Unfortunately, I don't know enough to confidently say I'll steal that for the book. But if I end up able to research a bit more and find that one useful, maybe I'll drop that in. I mean, I don't know if any specifically come to mind for the contents of this talk. I wish I could like quickly crawl through the book and see if there's any there already. But yeah, I don't have any that come to mind.
Yeah. It's interesting. I think like the mental model, I think, is easiest for parallelization, right? Because you're like, oh yeah, instead of doing things one after the other, I'm just gonna like, instead of one monkey doing it, I'm gonna have 4 monkeys,
Totally.
or whatever. But I like some of the other ones are a little they are a little more abstract, and it's interesting, I think, to think of like what helps us understand them, like, and know when to use them or anything. That'll be interesting. There was another question specifically about the submodel trick, and that one is one that is, I never hear about that outside of tidy models. Like it's, I feel like I mean, it's not, it's not something that can only be done in tidy models, but I only ever feel like I hear about it, and it's so dramatic. Like, it's so dramatic. It's like, why would you fit Like all of it, like you
Yeah.
have the model structure inside, right? Like you have the trees, right?
Hmm.
I think this is very interesting. So maybe how, like when you talk to people about the submodel trick, you're starting to talk about this book. What, how do people understand it or respond to it? Are people surprised? And then also there's a question like what do you need in terms of a grid? Like what are the rules in terms of like what kind of grid you use? David here has a specific question about tuning with
Mm,
a grid that that's like a max entropy grid. It's like instead of a regular
yeah.
like there's different ways you can make a grid. And like do people need to know anything special about their grids when they're doing the submodel trick?
Yep. Absolutely. I think, I mean, the first point about like not hearing about it a lot outside of tidy models, I think is like totally my experience as well. Many many folks have encountered this if they've worked with specific uh, model types like a lot. Like if somebody has been a GlimNet user for a long time or an XGBoost user, and they're trying to um, switch their workflow to something that's a little bit more agnostic to a given model. But if you've seen like the CV.glimnet or XGBoost has some sort of like automated cross validation sort of thing too, that's actually what's happening under the hood. The MLR3 folks, which is sort of a peer to tidy models, another way, um, another like standardized syntax for machine learning and tidy models, they refer to this as internal tuning. And they actually make use of all those different engines, internal tuning methods instead of the way that tidy models does it, which is we just fit one and then manually carve out the pieces that we're interested in working with. Okay, so in reference to specifically the kinds of grids that work here, we're specifically interested in working with regular grids in the context of the submodel trick. And so the way that a regular grid would work, I should have totally just like dropped in a quick like slide printing these out. A regular grid will take, let's say, a model with 1,000 trees and a learning rate of 0.1, which is another parameter for a boosted tree. To predict across other values of trees using the submodel trick, all the other parameters need to stay the same. So that learning rate still needs to be 0.1 for me to be able to chop out the first 100 trees and predict from it. If I'm varying other parameters while I also vary the parameter that is related to the submodel trick, so in this case, the number of trees, then when I cut out the first 100 trees, I'm not describing the right model or the one that I'm interested in evaluating. I'm describing the model that has all the parameters exactly the same besides this one parameter that enables the submodel trick. So using a space filling grid or maximum entropy grid, there's a lot of good statistical evidence about why one might want to do that, especially with smaller grid values, which is like the default setting in tidy models. You start off with a smaller grid and you can ratchet that up as a user if you want to. And so that's why space filling grids like you're describing are the default in tidy models, because there's some good statistical evidence about how likely you are to come across the quote unquote best parameterization of that model. So if you are interested in making use of the submodel trick, you need to transition your code over to regular grids.
Yeah, great. Thanks for explaining that about why the regular grids are the ones that let you do the submodel trick. Yeah. So Eric has a question. Eric noticed that Simon, you a couple times alluded
Mm,
to the fact that this data has certain characteristics to, like it has certain things that are true about it that mean it was super slow, but then when we did something, use some different approaches, it really sped up. So
yeah,
what are the types of data that people need to be aware of about how, if they have it, they can really make a difference by using some of these strategies?
right. Yeah, so in the book, there are a few different tricks, I guess you could say, or Yeah, tricks that that many specific modeling engines tend to have trouble with. One of them is highly correlated data. So if the value of your predictors are super correlated amongst each other, that's something that makes matrix calculus pretty difficult. Another one of those is many factor levels. So in categorical variables, if you have a bunch of different levels inside those variables, and then you toss it into a model, many of those will create a data structure where each level of that factor variable results in a column in the data that it's modeling on. And so that means an explosion in the size of the data that you're working with, and thus usually slowdowns in the model's effectiveness. The tidymodels is in the middle of shipping out a set of features for sparsity, which should help our users not fall into that trap by default. And so we can detect when there's many factor levels that will be split up into a bunch of different columns, and in those cases, implement a couple tricks to guard our users from that. And then the last one that the book makes use of is data that has nothing to do with the outcome. So if you just have straight noise in your predictor variables, some models will do their best to really try and find some signal there, and that can tend to make gradient descent take a long time because it's like starting and stopping, trying to find some convergence criteria, and doesn't tend to get there.
Nice, nice. Yeah, those are really great to be able to outline. So Abby asked a question about so you tried a bunch of different things, right? Or not you tried. You
Mm-hmm.
like implemented several strategies. In this particular example, what made the biggest difference? And is that generalizable? Like how do you know which ones of these make the biggest difference? Like which of these are the most important?
Totally. So I'm thinking about, I think this is a great question. In the book, I'm thinking about like starting off each of those chapters with like, okay, how much of this speed up that we saw is attributable specifically to this one thing. They do have interactions with each other, such that using them in certain combinations, you don't really get the multiplicative effect. With parallel processing, when things take a long time, your speed up is almost the factor of how many cores you're splitting up the computations across. So like if I'm splitting up across 4 cores and the thing takes an hour, it might take almost 15 minutes. There's always some overhead associated with distributing computations across cores. But it's something like a factor of the number of cores you're splitting across. The documentation for the tune race ANOVA function has some nice benchmarks where they fix everything. In the first example, use tune grid, and then the second one use tune race ANOVA, and I think it's something like 3 or 4 times speed up there. The submodel trick is kind of a funny one, and I poke at this in the book. Like you can make some ridiculous speed ups if you want. Like if I'm just tuning a boosted tree, I can evaluate 1,000 trees and 999 and 998, like 1,000 different settings of that parameter using one model fit. And that speed up is absurd. Like it is unreal how much that speeds up the result. And at the same time, like practically it's not super useful to like actually evaluate all 1,000 of those. But that can kind of be as extreme as you want it to be. Yeah, I mean, all of them are. We don't tend to see situations where like one of these helps by 2% and the other is like accounting for all of the change when you toss them together, as long as all of them still apply. Like there are many models in the tidymodels for which there are no submodels or parameters that support the submodel trick. And there are some models which, when distributing across cores, have some struggles with communicating with the parent R process, or the process that you're actually working in, which can mean often that there's really not that much of a speed up.
Yeah, great. That's great. All right, so we've got, I think, one more question. Feel free to type in another one if anything comes to mind for you all. We've got another question here from someone who is in grad school, uses R a lot, uses R mostly for statistical analysis, and is like, this was interesting. How does this relate to me? And I'm gonna drop a link to the book I worked on together with Max on tidy models that outlines like a kind of a categories of models, like why might you train a model, for what purpose might you train a model, and the three that are in there are like you train a model to describe behavior, like it's a descriptive model. The second one is like an inferential model where you are using the parameters of the model itself to say something about what is causing what, like you're using the parameters of the models itself to say like a hypothesis, like a statistical test or something. And then the third kind is predictive models, where you are training the model to make a prediction. And I'd be interested in your take on this, Simon. Like when I have been like, I need to just chug through this, I need to make this faster. Like, how do you think is that playing out for the purposes that people train their models? Like, is there intersection there? Is this most useful for one kind of model? Do maybe when you think back to like when you were helping R people in
Mm-hmm.
your job, and like people came in and were like, I need help with R
You're
on this
right.
project,
Yeah.
like if you're like, well, if I could have made this faster, what do you think? Does it apply to all reasons you might make a model? Does it apply to one more than another? What are your thoughts?
Mm-hmm. Well, I think that's a great place to start. And I would refer the asker of this question to that chapter in the book, because I think they'll probably get a lot out of that. In general, users of the tidy models, well, in general, the tidy models is mostly purpose built for folks that are doing predictive modeling. And so these optimizations describe changes that in the predictive modeling setting, you're not really sacrificing anything in order to get there. In the case of like inferential modeling, the goal of like describing the world, or like coming to coefficients that you can use to like learn about data generating processes, these tricks aren't necessarily helpful at getting you to that place any faster.
Yeah, I think that's certainly been my experience. Dan shares something. I can think the exception to that is when you're like bootstrapping to
Mm-hmm.
then do inference, like on the results of the bootstrapping. So I think when that's kind of, I think I would have said the same thing you said, Simon, right there, of like, I think this is mostly for predictive modeling.
Mm-hmm.
But you can use predictive modeling through bootstrapping um, to get to inference, like to
Yeah.
use the predictive model for inferential purposes in that way, which I think can be pretty interesting as well. And
Mm-hmm.
then you're like, if I'm doing this 1,000 times, I really, yeah, like I do need to now start talking about doing this quickly and efficiently.
Mm-hmm. Yeah, I guess I should add on like that. That's historically been the case, that we've like mostly purpose built tooling for predictive modeling specifically. We've spent some effort in the last couple of years, for one, thinking about the kinds of assumptions that folks doing causal inference make about what machine learning model development looks like, and the ways that tidy models violates those, and in order to try to resolve those differences, and make all this tooling available to folks that are doing causal inference. And then also we've been spending a good bit of time on like Bootstrap 632 methods, which is related to this comment about bootstrapping for inference. So if you're interested in that specifically, I would give that a Google and find it in the Tune package.
Nice, nice. Well, once again, Simon, thank you so much for sharing with us about with the work you've been doing, about the book that you're in the process of writing. It was really great to get to hear from you and to get to learn more about this and see the vast speed ups that are possible. So it was
Yeah,
really
I
great.
appreciate y'all having me.
Yeah. And as we wrap up, I'll say thank you to you all for coming. We do have a talk next month, about a month from now in February, that is from a local Salt Lake person. So Bart Polson will be here speaking next time. You may have seen Bart around on like LinkedIn Learning or at other places, and he's going to be giving us a talk about how to make sure that the work that we do with data is actionable. So take a look. Let me drop a link for that here, and then so that you all can find that easily. Whoops, I'm having a trouble pasting a link, great. Okay, there we go, is a link there if you want to join us next month. So happy January. Hope you all are doing great, and thank you again so much for coming.
Thanks, everyone.
Thank you.